What's the name of that module? The time domain representations for LTI systems. Time domain representations for LTI systems we have to do now. Time invariant property. Let us assume any system is having linear time invariant property systems. Let us represent now. What's the name now? Time domain representations for linear time invariant systems. Let us study. Out of 5 to 6 property we studied, we'll take these two seriously. Linear property and time invariant. We'll see how the representation is being done in time domain. That's the name of this module. Throughout this module, what we'll do? We will analyze linear time invariant property systems, how it is being represented in time domain. That's what second module we will do, which satisfy linearity and time invariance. Whichever the system which satisfy these two properties, linearity and in time invariance, are called as LTI systems. In our design, always we assume that system, all our practical applications, we assume that by default it is linear and it is time invariant. We never assume any system as non-linear. We never assume any system as time invariant, time variant. We always assume, design anything, we assume it as linear and time invariance. What do you mean by linear? For example, I am talking now, I am teaching you, you are following the same. That is called linear. Charan, then that is called linear. Are you understanding? Right? Arvind Reddy, just forget everything, just listen, don't do anything. I make note of it. In between, I'll call the attendance also, don't worry now. Whenever I want, I will call. Please listen. Please understand this important concept, then problems become easy. Within 1 minute, you can finish up. Please. Now, so that is timing. What is it? Linearity. Now, second point. In this module, we describe what we will do in this module, different time domain representations for LTI systems. First, we assume this as LTI systems throughout module, and then we describe different way of time domain representation, not frequency. What is time domain representation? X of n input, y of n output, or x of t input, y of t output. That is time domain representation. Next, third point. The representations means, what do you mean by representations? That relates the output of signals to the input signals. When both the signals are represented or analyzed in time. That means when both, last point, when both are analyzed as time domain only, not frequency domain. So that's what we will do. Now, last point is there exist 3 ways, different methods of representing any LTI system. This is very, very important, 3 different methods. There exist 3 different methods of representing an LTI system in time domain, throughout time domain. They are, number 1, very important. How do you represent in time domain? In terms of impulse functions. In terms of impulse function, throughout now we are dealing these impulse functions. Note down this parameter. What do you mean by impulse function? Delta n. Impulse is one where at n is equal to 0, all its finite energy exists. At all other points, its value is 0. That is impulse functions. In that terms of impulse functions, we'll deal all. We'll represent input, we'll represent output, we'll represent h of n. Second method is using difference and differential equations. It is in this module. Then third method, how do you represent the LTI system? Using block diagram representation. Are you understanding? So if you understand these 3 terms, in this module we are representing LTI system in terms of impulse function only. Note down the first one. Every minute I will use these impulse functions, impulse response now, from now onwards. It is very interesting. So that is module 2 now. Now let me go to the first one only. First one, what is next? General, what do you mean by impulse response now? General impulse response representations for LTI systems. What do you mean by LTI system? See that diagram? LTI system, consider which has input x of n, which has system impulse, system response is h of n, let's say. Let us not worry about h of n now. Worry about input and output only. Then y of n, output of the system, LTI, linear time invariant system, is x of n convolutions of linear convolutions now into h of n, which is nothing but convolution sum. This is very, very important. If it is discrete, this is the input, this is the output. Half of the module is convolution sum. For example, if you are describing continuous time signals, it is discrete now. If it is continuous means what? Same LTI systems with input instead of x of n, what is the input? Host. If it is continuous, this is discrete, x of n is input. If it is continuous signals, what is the input then in place of x of n?
X of t.
X of t. That's all you remember. Then what is h of n? System functions. It is h of t. Then what is output functions in case of continuous? Y of t. Then you have to do again linear convolution, that is x of t into h of t, and which is described as convolution integral. Right, this diagram you remember, x of n is input, h of n is system, y of n is output. Now I am saying the same only. Let us consider an LTI systems which has input x of n in case of discrete, or x of t, and system function is h of n or h of t, and as output response is y of n. Now, second point is important. See this. If you remember this, based on this only problem we are doing. Even you can read out also. If the input to the system, linear system, is expressed as weighted superpositions of time shifted impulse. See this underline word, weighted superpositions of time shifted impulses. What do you mean by impulses? See that word. I told you there are three ways of representing system. In that, in terms of impulse function, I said. That's why that word. In terms of impulses means input you should express as weighted sum of time shifted impulses. This time shifted impulses I will tell you in the problem. You just remember this word now. That's all. If the input is time shifted impulses, then the output also gives the weighted superpositions of system responses to each shifted impulses. That means you are getting output now. That is also in the form of weighted superpositions of time shifted impulses only. That's why LTI representation, if you represent in terms of impulses, you will get output also in terms of impulses only. What is exactly that time shifted impulses? We'll see in the problem later. Right now, remember this word. Are you understanding? Next point. This weighted superpositions is nothing but convolution sum. Just now I told you in the diagram. In case of discrete, right, that's what I am saying. This weighted superposition is known as convolution sum. For discrete time sequences, that is y of n is equal to x of n linear convolutions of h of n. Same if it is continuous. Same weighted superpositions as convolution integral. First half I do. You also remember first half. Next half is wherever time is there, you write discrete as continuous and call that convolution sum, you call it as convolution integral. For continuous time signals, that is y of t is equal to x of t into, that is convolutions of y of t. That's all. Right now what you have understood? If it is general impulse response representations for LTI system is like this, consider LTI where x of n is input, h of n is system functions, y of n is output. Then that's what I am telling in first two lines. Next point is, if input is, remember these words, to the linear system is expressed as weighted superpositions of time shifted impulses. If input is expressed in impulse functions, output is also in terms of impulse only. This weighted impulse superposition is nothing but convolution sum for discrete time, y of n. And it is nothing but convolution integral, that is the word, for continuous time signal. See that contradict word, convolution sum for discrete, convolution integral for continuous time signal. Now, let me solve a problem. You will understand what is exactly weighted superpositions of time shifted impulses now. What is the next heading? This they have asked. Explain or discuss or how do you represent impulse response representations for any discrete time signal x of n. See this problem. Let us consider any discrete time signal x of n as usual. I'm taking x of n discrete. In terms of weighted sum of time shifted unit impulses. What do you mean by that? Is giving x of n as, now take one sequences. -1, 2, 2, 1.5. What's the meaning? This like is giving a sequence, no? Right in terms of diagram. What is the arrow indicate? At 0, its value is 2. That's the meaning. X of 0 is 2. Amplitude is 2. That's the way. Right side arrow is 1 index. At 1, its value is 1. At 2, its value is 0.5. Then at 3, it is 0. Similarly, left side arrow is -1. Now see that at -1, its value is 2. See, I have written at -2, its value is -1. This is how I am representing first one sequence. They are giving x of n in diagram. If you know this how to write, later problems are easy. Please remember and try to know this. Now, what he says is now, how many samples are there in the diagram? See the diagram, how many samples are there? At -2, it starts from one sample, -1. At -1, second sample is 2. Like that, third sample is 2. Amplitude, fourth sample is 1. Fifth sample is 0.5. That means there exist 5 different samples. Now, these 5 samples of x of n, you should write in terms of impulses. Separate. How do you write? Before writing that, see that right side corner, just remember this impulse functions, because in terms of impulses I am writing. You know it 100 times I have written. What is delta n? Delta n is nothing but, see the diagram. Its value is 1 at 0. All other points, its value is 0. You know this in Z transform only. Then what is required? Delta n plus 2 required actually in this problem. What do you mean by delta of n plus 2? Delta of n plus 2 is nothing but the impulse delta n is shifted, advanced shift here. Plus 2 means it is advanced by 2 seconds early. That means at -2, its value is 1. Shift to the left side by 2. That is what delta n plus 2. That is what's shown. Now with this information, now let me start. Split this, your given input as 5 samples different. Impulse sample. How? First, these signals can be splitted as shifted impulses using this formula. What is that? Let me start from x1n. First, x1n is equal to, where exactly your first sample start? Your first sample start in your diagram at -2. Let me write that. x1n is equal to x at -2 into, in terms of impulse, delta of n plus 2. Do you have any doubt here? What do you mean by x of -2? X at -2, index in the -2. What is x at -2 value? It is -1. See that sample? Then, what is the value of shifted impulse delta n plus 2? Delta of n plus 2 is 1. That's the value of impulse. That means impulse exists at n plus 2 only. At all other points, that's the meaning of delta of n plus 2. At all other points, its value is 0. Therefore, its value is 1. Now, -1 into 1 is -1. That is called x1n. Write that as x1n. Now, see, I have written. See that? Write that first sample separately in terms of impulses like this now. See, x1n is equal to x of -2 is -1 into delta of n plus 2 is similarly, I want second sample. What is second sample? Second sample in your x of n exists at which point? At the index -1. X at -1, its value is 2 into, what is in terms of impulse if you write at -1, what is the impulse? Delta of n plus 1. Now see, I am writing that one. Now see, write x of 2, x2n. Similarly, second sample you write in your diagram. That is equal to x at -1 into delta of n plus 1. What is x at -2, -1? See now, x at -1, its amplitude is 2. The 2 into, what is delta of n minus now? See, that is 2. 2 into, what is in terms of impulse if you write? It is advanced by 1. Delta of n plus 1, that is 1. Therefore, 2 into 1 is 2. Therefore, its value is 2 at -1. Similarly, now, x3n. Third sample is what? Which one? X at 0, third sample you are getting your input. x at 0 is 2, and that I am writing like this. Now see, x3 of n is equal to third sample is equal to x at 0 into delta of n. Now see, x at 0 is which one? What? 2. 2 into, in terms of impulse, if you write delta of 0, delta of 0 is, now see, x at 0 into delta of n. X at 0 is 2, delta of 0 is 1. That is equal to 2. That's how we'll get third sample as 2. Then, fourth sample. What is the impulse of fourth sample in your input? Fourth sample is x at 1, its value is amplitude is 1. Now, how I am writing? Right now. Now, x at 1 is, now see, fourth sample is x4n is equal to x at 1 into, in terms of impulse, if you write, impulse is delayed by 1. Because see, delta of n minus 1, see, 1 is existing after 1 delay. Are you understanding? At 0 it is delta n, at 1 index it is delta n minus 1. That's why delta n minus 1 I am writing. Therefore, x at 1 is 1, 1 into delta n minus 1 is 1, 1 is to 1 is equal to 1. That's how we'll get fourth sample as 1. Fifth sample is last sample. That is x at 2 is equal to 0.5 into delta of n minus 2. That's what I am writing. Now see, x at 5 is equal to x of 2 into delta of n minus 2. Shifted function that is. Therefore, x at 2 is 0.5 and x at delta of n minus 2 is always 1. Unit sample there is equal to 0.5. Therefore, separately I am writing all impulses. Now say this is how I am writing separately impulses. If 5 samples are there, in terms of shifted impulses, separately I am writing 5 times each individual sample minus 1, 2, 2, 3, 1 and 0.5. Are you getting it? This is how I am writing input x of n as shifted impulses, 5 shifted impulses. If they are giving 6 impulses here, 6 pulses, what I should do? I should write 6 times pulses, shifted pulses. Shifted x1 and x2 and x3 and x4 and x5 and x6 and that's all. Now, finally, add all these things, write in summation. Finally, weighted sum of time shifted impulses, that term I told you, weighted sum of time shifted impulses I told you in beginning, no, can be written as, now combine all these and write x of n is equal to, how do you write first one? First one starts from where? It starts from C now, x at minus 2, delta of n plus 2, that you write first one. Then second one is x at minus 1 into delta of n minus n plus 1 plus third one, see that x of 1 into delta of n, x at 0. Fourth one, x1 plus into delta of n minus 1 plus last one, x2 into delta of n minus 2. That is what in the figure. Now see that first it starts from minus 2. That is what x of minus 2 into delta of n minus 2. See the figure only and write. And x of minus 1, delta of n plus 1, x at 0 into delta of n, x and 1, delta of n plus 1, n minus 1, x at 2, delta of n minus 2. Now, write all these as summations. How do you write? Final line. That's what convolution. We have written already. X of n is equal to, summation starts from where to where? Summation starts from k is equal to minus 2 to 2. What is that? When you now say important. Summation starts from k is equal to minus 2 to 2. What is the meaning? Minus 2y at k is equal to minus 2. What you will get? First term you will get x of minus 2, delta of minus of. What is that? Now x of minus 2 is equal to x of minus 2, delta of minus 2 is delta plus 2. That's how we'll get first term. Now see, x of minus 2, delta of n plus 2. Then when k is equal to minus 1, x of minus 1, delta of n minus 1 minus 1 of minus 1 of minus 1. Then you will get this second term. Now see, x of minus 1, delta of n plus 1. Similarly, when k is equal to 0, x0 into delta n. Similarly, last term, when x is equal to, k is equal to 2, x2 delta of n minus 2. That's how you will get last term. See now, x2 delta of n minus 2. That is why this is called as, in general, any discrete time signal x of can be expressed as, remember this expression already used in your Z transform. X of n is equal to, generally, k is equal to minus infinity to plus infinity, x of k delta of n minus k, which is nothing but convolution sum expressions, which we have already used. Call this as equation number 1. Remember this equation always. Since x of n is equal to, in this case, minus 2 to plus 2, why I am using is, your signal starts from minus 2 and plus 2 it ends. If it is minus 3 to plus 3, it is k is equal to minus 3 to plus 3. Since general I am taking this as minus infinity to plus infinity, remember these equations final. This is also called as convolution sum equations. They will ask you these derivations for 8 marks or 6 marks. You should find first finally x of n as summations k is equal to minus infinity to plus infinity, x of k into delta of n minus k. That is why this is called as, x of n is described in terms of shifted impulses. See this word, weighted. Input is expressed as shifted superpositions of shifted time impulses. Is this. Now see, shifted impulses only, these are all. See, delta n plus 2, delta of n minus 1, n plus 1, delta n, delta of n minus. You write whatever given x of n, write present in terms of impulses. And finally write these summations. That's what the answer, right?